My first ISBA experience was a rather negative one. I was in a cab in Turkey, I think, with Steve Feinberg and Alicia Karakwiri, and they were telling me about this new thing called ISBA. And I was very negative. I thought, well, we really don't need that. Bayesian statistics is already becoming completely mainstream. It's fully embedded in all sorts of general meetings. We really don't need to secrete ourselves away into special private meetings. I still think that to some extent, but I couldn't have been more wrong about how valuable ISBA has been at growing this community. And the huge number of people here at this conference is testimony to that. So well done to those early pioneers of the society for having the vision to do this. Thanks to the organisers for giving me the honour of speaking in one of these lectures. After they invited me and after I accepted, they then changed the time limit. So I've got less time than I thought I would have originally, and you'll probably be glad of that. But in consequence, I'm going to concentrate particularly on methods and how they work rather than show you applications. The contents is somewhat crowded, but the general structure, don't bother to study this in detail. The general structure is I'm going to talk a little bit about the fundamental underpinnings of conditional independence and Markov properties, to introduce the subject of structural learning, which is the main point of this, and then talk about various classes of graphs and how we do structural learning in them. There's going to be quite an emphasis on decomposable models, but not exclusively, and I'll spend as much time on these last sections as I have when we get there. So thanks to pioneers of statistics who are here, the conditional independence has become one of the absolutely central ideas of our discipline. It's key to understanding the structure of multivariate distributions, and it's key to understanding the structure of samples of data. And in the early days, this was something that was studied particularly in relatively narrow areas of the discipline, but it's since become very, very widespread. So to remind you, the idea of conditional independence, we're talking about three random quantities, x, y, and z. And x and y are conditionally independent given z if written in this form, in Phil David's famous invented symbol, x conditionally independent of y given z means that if you already know the value of z, if that's background environmental information, if you like, learning the value of y tells you nothing more about x. And this means that any dependence between x and y is indirect. It's mediated through the values of z. And that's an idea that can be studied more abstractly. And Stefan Larritz's book is a wonderful representation of that formulation. But in probability terms, it's something quite concrete. It says that the joint distribution of x and y given z factorizes into the conditional marginals. And what we've learned is that it becomes really useful to represent conditional independence in a graphical form. Because I began in this in spatial statistics, my pictures are somewhat spatial in character here. So one of the early origins of this idea were in the attempts to extend to spatial processes the ideas of Markov modeling in time series. So we would have the idea of perhaps some spatially distributed collection of entities here, linked by pathways. We're trying to think about how to model the yellow node given all the others. And by analogy with time series modeling, in Markov chain modeling in time series, we might think that we want to model that distribution of the yellow given all the others as depending only on the red ones, only on the neighbors in the graph. And that's something we now call the local Markov property. If a graph has that property, if whichever node you choose as the yellow node, you have that property, then the local Markov property holds. In physics, statisticians became aware that these ideas were around already, and the idea of Gibbs distributions was present. And the Gibbs distribution, for our terms, is a distribution that factorizes as products over cliques. So in my talk, a clique is going to be a maximally connected subgraph. So this blue subgraph is an example. Here's another one, a maximally completed subgraph. And if the distribution factorizes as a product of functions of the variables in those cliques, then we call that a Gibbs distribution. So there we have two ideas, a graphical property and a factorization property. And one of the first early results in this subject was the discovery that these were, under conditions, equivalent. And that's something that spatial statisticians call the Hammersley-Clifford theorem. And with a little more time and a little more understanding, other kinds of Markov property were identified. These are all properties that are obviously true in a linear chain, thinking of a Markov chain model. But one idea is that if two variables are not adjacent in the graph, then they are conditionally independent given all the others. So the graph in that picture now is a graph of those that are not conditionally independent given all others. And then finally, the global Markov property is a separation property. I need 4 colors now. And if you look at this picture, there's no way of going from blue to yellow except through red. And it's if we can state that whenever that happens, we have yellow conditionally independent of blue given red, then this global Markov property applies. So there's several ideas there, 3 different graphical ideas and an algebraic idea. And the beautiful thing is these are all deeply connected. So we now have a more complete understanding of the connection between these properties in undirected graphs now, graphs without arrows on the edges. And very conveniently in English and in some other languages, these are in alphabetical order. F implies G, implies L, implies P. And under additional conditions, these are sufficient but not necessary. Under additional conditions, these are actually all equivalent. So this is telling us something quite profound. It's telling us that the idea that conditional independence has a structure. It tells us that we can manipulate it graphically. We can perhaps build algorithms that are themselves graphical. And that we can link these properties to underlying factorization properties so that we can prove results in the algebraic domain as well as in the graphical one. And also, I hope it's clear that the idea of conditional independence is absolutely key in Bayesian statistics because it precisely describes what variables tell us about other variables, what data tells us about parameters conditional on other knowledge. So when I just talk about the conditional independence graph, I'm talking about this graph defined by the pairwise Markov property. We draw edges between 2 vertices representing variables. We draw edges between 2 variables unless they are conditionally independent, given all other variables. Now, of course, these undirected graphs are not the only kinds of graphs that are important in statistics, and for reasons of time, I'll only mention one other class, another really important class, the class of directed acyclic graphs. Directed graphs are those where the edges are all arrows, pointing in one direction only. A directed graph in which there are no directed loops, we call a DAG. Equivalently, it's a graph where the edges can be numbered so that edges can only go from a low number to a high number. And there's a whole system of Markov properties and conditional independencies that hold for these graphs as well. And again, these can all be discovered fully in Stefan's book. The Markov property in its local form for a directed graph says the following, rather more complicated statement. Variables are independent of their non-descendants given their parents. So in my picture here, if we look at variable, the red one, its non-descendants are the 2 yellow nodes, and if we, and it is true, if the directed local Markov property holds, that red is conditionally independent of yellow given green. And the factorization property, of course, is the property we always use when we're building models, that the joint distribution of all variables is the product of the conditional distributions of variables given their parents in the graph. So graphs occur all around statistics. I mean, there's 650 people here. There are many, many posters and talks. And graphical ideas are going to be explicit or sometimes implicit in a very large fraction of the presentations and posters that we'll see. Obviously, they're important for visualization. They're obviously important for modeling. I'm today particularly talking about the use of graphs as outputs of inference, discovery of structure, and also, of course, they provide a big role in building algorithms. And many of the computations that we will be doing this week and talking about this week explicitly exploit the graphical structures and the conditional independencies that these graphs hold. Another key idea, and I hope we'll see quite a lot about this in this conference as well. Of course, we know that association and causality are different, but drawing graphs can really be a key idea in helping us understand the connections and the possibilities for causal inference in statistics. And indeed, drawing a graph immediately tells us why this is complicated. The possibility that we're trying to study the way a variable affects another, a risk factor for disease, for example, and the idea that there may be other variables, possibly unmeasured, that influence them both. And as soon as you draw the picture, you understand the problem. But my talk is not about these things. It's about learning. It's about structural learning. And I hope I've sold the idea to you that the graph is a really key, or the conditional independencies are a really key idea in understanding what a set of data is telling us, and that drawing pictures can help us understand that. So we have the idea that given data, perhaps to keep it simple, an IID sample of data from some from some multivariate distribution, we may be interested in inferring this conditional independence graph. And that's the problem of structural learning in machine learning language. And it's the subject of the talk today. So why do we want to do that? Well, first of all, the graph may be of direct interest. It may be the real subject of inference. If we try to construct pedigrees, for example, of human families, it's because we want to understand the pedigree. That's the genuine output. You could say the same thing about gene networks, for example. We're really trying to understand what's going on. The graph really is a representation of the science. But that's not always the objective. We may be looking for parsimony. We all know that estimating something as simple as estimating a covariance matrix becomes really difficult as the dimension increases. If there are p variables, then there are of order p squared covariances, and the larger p gets, and these days it does get very large, it becomes extremely difficult to estimate something as simple as that. And of course, if we know the dependencies have a simple structure, we can build that in and solve the problem, remove degrees of freedom, so that we have a chance of estimating things stably. So that's an indirect use of a graph. And then also, of course, informally, it's an aid to understanding. It's an aid to appreciating what the data is telling us, a sort of exploratory data analysis. So this is a kind of model selection problem. But it can be a selection problem on a huge scale. Because if we have v vertices, or variables, then there are v choose 2, v times v minus 1 over 2, possible edges that may or may not be present. Each of them may or may not be present in a graph. And so we have 2 to the power v choose 2 possible models. It's a discrete space, but one that becomes huge as v increases. But people have been drawing graphs as outputs, the results of inferences, for over 30 years now. This is the one I often use as an opening example, 31 years ago, where this was the summary of a set of analyses on a 2 to the 6th contingency table, so 6 binary variables. They happen to be prognostic factors for heart disease, and Edwards and Havranek displayed this graph as a summary of the results of their conditional independence tests. 6 variables, there were 2 to the 15 possible graphs, and this is the one they choose to display. Much more recently, I've stolen this graph from one of Stefan's presentations. This is a graph inferred from data representing SNPs. So the nodes are all SNPs here. And this is a forest, a collection of trees, fitted to that data using a minimum BIC criterion. To steal a slide from another person present at the conference, these were 2 analyses from financial data, so S&P equity data. I've shown them shown 2 examples here because it emphasizes that the graph, which of course is an important discrete structural representation of the dependencies, is not independent of inference about parameters. And so under different distributional assumptions and different criteria, different graphs may be inferred. And somebody I've worked quite a lot with on these models on these methods is Alan Thomas, who's interested in genetic epidemiology. And this was a graph he produced some years ago as a result of analyzing contingency table data relating to disease status, to SNPs, modeled dependently, of course, covariates, and some quantitative traits. So these are all visual representations of the result of analyses of data and are intended to convey to the human eye something about the pattern of dependence, so from which we can learn and start perhaps at least to generate hypotheses for future study. I think it's worth pausing just a moment to think, in the light of those examples and others, think about what structural learning is really supposed to deliver. Very often, we can't truthfully say there really is a graph. There's not a true graph that is sparse and simple, and if we only knew that, we'd really understand something. The absence of an edge in practice perhaps means more, not conditional independence, but insignificant dependence. So I like to think of these sometimes as more like modeling using sparsity assumptions in variable selection. It's not that we truly believe there are any zero regression coefficients. Life is often quite a bit more complicated than that. But that we choose to treat some of the betas as zero, we'll find out which ones are zero, and we'll build models accordingly. So this is a Bayesian meeting, and I'm only going to talk about Bayesian methods for structural learning. They're not the only methods there are. There are other classes of methods, and indeed in some ways other methods, non-Bayesian methods, are ahead of us in terms of being able to deal with very big data sets. But I'm particularly going to talk about Bayesian methods, and particularly among those that really try to deliver posterior probabilities. So these are not necessarily methods that simply set up an objective function based on some model that might be interpreted as Bayesian and then optimize it. And that's not delivering the power of the Bayesian paradigm, and it's not allowing us to do various of the things we would like to do from a fully Bayesian analysis. And although, of course, we'd like to do everything, we'd like to do the world, we're typically going to restrict the space of graphs to a subset of possible graphs. And those that have been particularly studied being things like trees and forests, DAGs, of course, and decomposable graphs. So I'm going to spend a bit of time talking about the problems of structural learning in these different situations. So let's talk about decomposability first. This has been very much studied. It's a subject in graph theory. It's a pure mathematical idea, if you like. But it's one that has profound statistical and computational implications. It's a funny word. We'll see in a minute why it's got that name, why we talk about decomposability. But if this is new to you, it's probably simpler to think of the definition pictorially in terms of one of these two words, triangulated or chordal. A graph is decomposable if and only if it has no chordless k cycles for k bigger than 4. So a k cycle is what it will be. It's a loop like this one here, 1, 2, 3, 4. It's a chordless cycle is a loop like that one which has no shortcuts. There are no chords connecting intermediate vertices on that path. So the graph on the left is not decomposable because there is such a circuit. The one on the right is decomposable because there is no such circuit. And you can see it looks like a collection of triangles, hence those two words. Such a simple idea, but one with very profound implications. Well, first of all, a graph is decomposable if and only if it has this rather indirect representation in terms of what we call a junction tree. So junction trees are graphs, new graphs, whose vertices are cliques. I've already told you cliques are maximal complete subgraphs, with the property that the edges, the cliques containing any prescribed set of vertices form a connected subtree. Now look at this picture here. Let's look for some cliques. 2, 6, 7, there's a clique. Okay, they're all connected. 2, 6, 7, there's a clique. And so on. There are 4 cliques in all, these things here. And I've connected them up in a tree. The tree is called a junction tree. And if you just mentally choose one of these 7 vertices, 3 for example, and look at where 3 lies in this picture, and you'll find that the 3s are all connected. And that doesn't just work for 3. We label the links of the tree with, we call them separators. They're the intersections of the adjacent cliques. So 2, 6, 7 and 2, 3, 6. The intersection is 2, 6. And you can spot the 2, 6 as the boundary between 2 of the cliques in this picture here. And these objects, these junction trees, for a given decomposable graph, they're not unique. There may be many of them. And the key, the real thing that, particularly for us, makes the idea of decomposability so important is this rather beautiful factorization. So we're now linking together distribution theory and graphs. So if the distribution of a random vector has a decomposable conditional independence graph, then its joint distribution, P of all the variables, the joint full multivariate distribution, factorizes as a product of low-dimensional things here, low-dimensional marginals, a product of all the clique marginals divided by the product of all the separator marginals. Right, an extraordinary thing. It's if you've ever done first-year probability, you've met it because you've met the idea of a Markov chain. And this is the defining property of the distribution of a Markov chain. And of course, writing these conditional probabilities as joints divided by marginals, we see that a factorization rather like that. And that's exactly what we're seeing in this more general definition. Essentially, decomposability allows you to take this Markov chain-like factorization and spread it out through the branches of a junction tree. So decomposable graphs, joint distributions, have very simple structure. And that is the key to many, 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 many things. The computational significance is that we can exploit that in algorithms for fitting models and for performing inference on parameters and so on, and giving dramatic speeds up, especially when the cliques are small. There's lots of important statistical significances from this. I mean, it's classical that that you can do maximum likelihood estimation explicitly on contingency table models when the graphs are decomposable. That you can do exact tests. We're going to see today that this gives dramatic speed ups in structural learning. And for Bayesian, something particularly beautiful, the idea that it gives us, in decomposable graphs, we have a very clear idea of what are the natural priors on parameters to have in these graphs, and giving us priors that are both philosophically attractive but also computationally tractable. So it gives us a framework for the construction of consistent prior distributions. Of course, if all graphs were decomposable, this would be wonderful, but unfortunately they're not. In fact, very few graphs are decomposable. All small graphs are decomposable. As soon as you have 4 vertices, you start to lose some, and as the number of vertices increases, the proportion of the graphs that are decomposable becomes tiny. Here are the 3 smallest non-decomposable graphs, the 3 ways of connecting 4 vertices to give you a chordless cycle. Now, if we knew nature was decomposable, life would be beautiful, but it's not unlikely that nature's kind enough to do that for us. Well, does this matter? Well, we can always, given any non-decomposable graph, we can always fill in edges so that it becomes decomposable. So imagine you're analyzing data and this was the real structural graph, and that's what you'd like to find, and you're going to be forced to find this one instead. Well, how much would that really matter? Providing our model allows arbitrarily small interactions, we may lose little by assuming decomposability. Well, that's hand-wavy and wishful thinking, but it's been firmed up with a real theorem. Thanks to Fitch and Jones and Massam, who showed that in a Gaussian case with particular priors, something about what happens asymptotically if you fit a decomposable model to a non-decomposable distribution. And the nicest, first of all, the main statement is that the posterior converges to graphical structures that are minimal triangulations of the true graph. In other words, my wishful thinking picture just back here was the right one. If you perform Bayesian structural learning under those assumptions, when that's the true model, what you'll get is things like this. There may be several minimal triangulations. A minimal triangulation is a triangulation which adds the smallest number of edges needed to make it decomposable. There may be many such triangulations. They will typically all have positive posterior probability, even asymptotically. But if you're interested in the graph simply as ensuring stability for covariance estimation, that doesn't matter because the resulting fitted covariance matrices are all essentially the same. And there really are tremendous advantages in assuming decomposability, not just for computation in fitting it in the first place. The decomposable structure turns out to be key to all sorts of things you might do with the model. Evaluating its fit, predicting from it, sampling from it. The fitted decomposable model is something you can really use. A fitted non-decomposable model is sometimes something that's as hard to use as it was to find in the first place. So what's the setup for Bayesian graphical model determination then? We'll just talk about IID data here for multivariate distribution. What are the unknowns here? There's an unknown distribution which is governed by a graph describing its conditional independencies and parameters. So the natural hierarchical model for this setup is that we're going to have a prior on the graphs, a prior on parameters for each graph, and a likelihood describing the data under that assumption. And the Bayesian problem of joint structural quantitative learning is about inferring that joint posterior distribution, the joint posterior distribution of the graph and the parameters. And of course, we have then issues about our choice of prior and for the graph and our choice of parameter priors. It's very commonly going to be the case, just to emphasize this, it's very commonly going to be the case that when you change the graph, completely different parameters will be needed. Typically, the denser the graph, the more parameters are involved. The subject of priors on graphs is a long-standing one. People have made different choices. Many people simply ignore the issue and assume it to be uniform. More recent suggestion was to control the prior on the size of the graph and then distribute that probability equally among all the graphs with that size. That's number of edges. We might ask, is there a more canonical or conjugate approach than just these rather informal ideas? And what might we be looking for? Well, reminding ourselves of this beautiful factorization of the likelihood, essentially, into a product of clique marginals over separator marginals. The kind of prior on the graph that would make life simple would be one where the prior for the probability of G itself factorizes in the same kind of way. And one of the lovely example of the capacity of this area to generate beautiful results, thanks to Simon Byrne and Phil David a few years ago, who considered this idea of having a Markov property on structure. And their assumption looks a bit abstract, but let's go through it. G is a graph. G sub A is the graph restricted to the subset of vertices in A, and similarly for B. And the graph is an unknowns thing, so we're talking about distributions on that graph. And if G restricted to A and G restricted to B are conditionally independent given this, then we say this structural Markov property holds. Now, what is this condition here? This funny-shaped U of A and B is the set of decomposable graphs, we know what they are, for which AB is a decomposition. So there's two new ideas here. There's the idea of a covering pair and the idea of a decomposition. A covering pair is just the ordinary pure math idea of covering. That is, AB is a covering pair if its union is the whole set of vertices. This is a decomposition if the intersection is complete and separates the rest of A from the rest of B. This picture tells the story. So in this particular picture, the A vertices are those in this rectangle, the B's are these. The intersection is that triangle drawn in green, and that's a decomposition because it's complete. All the edges in that intersection are connected, and it separates the yellows from the blues. Because that's an idea about Markovness, the idea that given this separates the remaining vertices, it says that we would like, philosophically, we'd like our uncertainty about the edges over here and our uncertainty about the edges over here to be independent. And that's what this property demands. Well, that would be all very well but useless if it didn't really lead somewhere. And the point is it does. It leads to exactly the kind of structure, factorization structure we would like. They show that a graph law is structurally Markov if and only if it can be factorized in this way. And what these phi's are arbitrary positive set index parameters. So any prior which has that structural Markov property can be written in this way. And that's really quite flexible. That's really quite powerful. And all such graph models have that conjugacy property I described. Compared to that, this is a very minor little extra bit, but if you slightly change the condition there, restrict to decomposable graphs for which that intersection is a clique in one side, let's say A, remains a clique in GA, then we're going to call that the weak structural Markov property. That places fewer conditional independence constraints on pi. Okay, that's a smaller set of G's. Therefore, this is a fewer conditional independence statements that this determines for us. So potentially it might lead to a richer class of graph priors, but we'll see in a moment that it's still a usable thing. So just to clarify what that is, here are some pictures. The vertex set are these 5 red dots. A is the 4 on the left, the square on the left. B is the triangle on the right. I'm conditioning throughout on the A and those two being connected, because we want it to be a decomposition. And I'm also conditioning on the graph that A intersection B remains a clique in GA. And that leaves us with 16 possibilities for GA and 4 possibilities for GB, these dotted lines. And so the weak structural Markov property would say that your choice among those and your choice among those have to be independent for every such A and B. And the remarkable thing is this can still lead to a factorization property, and with a slightly more general, because we can now have different functions on the denominator and the numerator. And that extra flexibility has already been used in computational work by Born and Karen. So this idea underlines what we saw right at the beginning, where the graphical properties and the factorization properties coexist and have implications between them. So it's a beautiful further episode in that story. And there you see the kind of conjugacy we would then get. Right, let's move on to talk about computing. For trees, there are explicit algorithms. We can do perfect simulation for models on trees. And it would be a beautiful thing if you could use these strong and powerful properties of decomposability here to find perfect samplers for Bayesian decomposable graph models, but there's really no progress on that. So we're looking at MCMC again, and we'll do the usual thing. We'll construct a Markov chain to have detailed balance with respect to the posterior we want, and we'll sample from it. Again, decomposability helps us because we can tell mathematically what kind of perturbations we can make to graphs and still keep them decomposable. So there's quite an old result by Stefan Lauritzen and colleague, and even, well, not quite so old result that I'm partly responsible for, that tells us what edge moves can be made that maintain decomposability. Because if you want to conduct a Markov chain and run the space of decomposable graphs, you don't want to be jumping outside that space. And these kind of moves, and it includes some multiple edge moves, certain kinds of multiple edge moves that completely connect vertices that are not currently connected or completely disconnect those that are. Certain multiple edge moves can also be characterized in this way. And you can efficiently represent those moves using a junction tree representation of the graph. These moves make only local changes to the junction tree, but they can change its topology locally as they do so. Now, it turns out that topology change is actually a bit of a performance, quite damaging in performance terms. And we recently found a simple way to speed up the sampling quite dramatically by cutting out the need to change the topology. And we do that by a trick, treating the junction tree itself as part of the model parameterization. And that means augmenting the model so that we distribute the prior probability on a particular graph equally among the junction trees that represent that graph. And that is a useful idea because we can count the number of such graphs so we know what probabilities we're assigning. In the interest of time, I shall speed forward a little bit, but this is a sort of, what we're getting here is it's a perfect alignment of several nice things that give us computational performance. We've got this pre-testing for maintaining decomposability. We have simplification of likelihood ratios because of that clique separator factorization. We're going to use the junction tree as the state, and we could do some certain multiple edge moves. And this allows effectively sampling models of a moderate size. And it's not the only way to sample decomposable graphs by local changes, but it's one of the most explored. Let me just a quick change of gear to show you that working. So here you're seeing a sampler running in real time, slowed down a bit by the need to render the graphs. This is a model with 50 vertices. It's simulated Gaussian data, and I think you'll begin perhaps to see what the true model was. The jittering you're seeing is partly just the randomization, partly just the rendering. But you can see quite a lot about the way this is sampling from this picture. You can see edges that come and go. Of course, the frequency with which they're present is estimating a posterior probability, and so on and so on. And we can, of course, evaluate joint distributions of all sorts of coexistence of edges. The true graph was that sort of lattice structure that you can see there. So that's 50 vertices, and we'd be reasonably confident running that kind of thing on a somewhat larger situation. Let me say, I haven't talked about parameters here. In early work, people tended to use reversible jump type or other transdimensional sampling to jointly sample from this variable dimension posterior distribution. But in order to try and scale up to larger problems, very early on, people started to use conjugate hyper-Markov priors for the parameters so that those could be figured out. And what you get then is that the metropolis ratio for updates to the graphs can be simplified into a locally computable form. So these so-called hyper-inverse Wishart priors have been used for variance matrices in Gaussian models and hyper-Dirichlet for the multinomial case. And there's been a lot of work on choice of hyperparameters in those priors. But they only go so far, and it's still true that we can only deal with quite moderate graphs here. So there's accumulated evidence that MCMC, using local moves, is good at recovering low-dimensional features, such as edge inclusion priors, edge inclusion probabilities. We can be fairly confident in the estimated values of the posterior probability of a particular edge being present, for example, or small probabilities of small combinations of particular edges. These kind of models in larger graphs are poor at recovering global properties because of really severe mixing problems. And that motivates a powerful idea, really beautiful idea of using the edge inclusion probabilities estimated online to drive a stochastic search algorithm which is now an optimization method for trying to find high posterior probability graphs. So we're moving beyond sampling now, but using sampling-based methods in order to conduct our optimization. And this Fink's method, feature inclusion stochastic search, has proved very powerful at hitting high posterior probability graphs, and it's good for prediction tasks. I think it's still true to say we don't really know enough about how well different approaches cover regions of high total probability. One of the key ideas in sampling these high-dimensional graph spaces is, of course, that the map estimate, the highest posterior probability graph, may or may not be representative of a region of graphs that are all of high probability. Let me move on to non-decomposable graphs. Even if the graph's not decomposable, we still have a similar factorization. But the sets in the numerator now, they're called prime components. They're maximal subgraphs that can't be decomposed, in the sense I've talked about, but they won't necessarily be complete. And this was explored in a statistical science paper about 10 years ago. And the additional difficulties are that the normalizing constants in those non-complete prime components don't have closed form. So you have to do Markov chain sampling within each step of the main chain in order to estimate them. And those calculated values are very high variance. So when you make, further, when you make single-edge perturbations to the graph, there is no guarantee of significant cancellation in the likelihood ratio. So these difficulties really add on computer time. In that paper, you can see the time scalings are enormous for still quite modest graphs. And their conclusion at the time was that posterior sampling was not practical for problems with more than about 15 nodes. And they resort to heuristics like stochastic shotgun search. Some of those difficulties have been ironed out later, and the need for MCMC and those normalizing constants has now been limited. But it's still the case that MCMC sampling for decomposable graphs, non-decomposable graphs, is very, very much harder. The stochastic shotgun search idea proceeds by starting with a graph, selecting graphs that differ by one edge from it, computing their unnormalized posterior probabilities, retaining the top ones, and then proceeding from that, among those neighbors, take the ith graphs as a new starting point, running little MCMCs, and so on. So it's a heuristic. It works rather well, and it's been improved and further explored in other papers. But it is a method of optimization, not a method of sampling. I think I'll skip the illustration stolen from that paper. Another way to approach the non-decomposable case is to remind ourselves, at least this is in the Gaussian case, that all conditional distributions in the multivariate Gaussian are, of course, Gaussian and linear. The mean has a linear structure. So that the problem of fitting a graphical Gaussian model is also the problem of fitting a lot of regressions. And you could simply do that job, fit multiple regressions, for example, by Bayesian methods, Bayesian sparse regression methods. You end up with a lot of conditional distributions of variables given others, and you need some way of piecing them together to deliver a single inference. And there have been various approaches to doing that, combining separately fitted sparse regression models to form a graphical estimate. And these have been applied to quite large data sets and appear interpretable. But there's a real, we've clearly moved some way from the pure Bayesian paradigm of fitting the model we originally thought of in this case. And there's been a lot of work on non-decomposable models, and which there isn't time to go into now. So we know a lot more about fitting non-decomposable models, but it's still the case that they are very much harder to fit than decomposable ones. I'll say a little bit about trees, and then I must wrap up. A tree is a connected, undirected graph with no loops. And if it's not necessarily corrected, we call it a forest. These are themselves decomposable graphs. For a tree, the junction tree is essentially isomorphic to the graph itself. except for the ends, the leaves at the ends of the branches. So of course, there's an intimate connection between junction tree algorithms and algorithms on trees. In a tree, the likelihood will always factorize in this way. That's the decomposability condition. And that's essentially a product of edge probabilities divided by a product of vertex probabilities. And so when we come to do posterior inference, the posterior divided by the prior is essentially a product of Bayes factors for dependence along the edges. And that structure is something that's amenable to perfect simulation, I mentioned earlier, because we have powerful algorithms for random spanning trees that can exploit that kind of structure. And that's been extended to tree priors that are themselves decomposable. Unfortunate choice of words, but that factorize again in this way as a product of weights of edges. And that works for trees, and it works, but if you do a little bit more work, it works also for forests. I think I shall have to skip the small section on DAGs. I'll just briefly mention what the difficulty is with DAGs. This is a situation where we wish to fit a DAG model to data that doesn't know anything about the directions. The pure form of this problem. Fitting DAGs is particularly important because of real or possibly imagined causal interpretations. And of course, there's a huge literature on Bayesian networks which exploits these models. The complicating factor in fitting DAGs is this problem of Markov equivalence. Two different DAGs can imply exactly the same set of conditional independencies. This is not true in an undirected graph, but it is true in a directed graph. So these two DAGs, so this DAG is equivalent to this one in the sense that the set of conditional independencies that are true in this one and this one are the same. This, here again, I've gone from one DAG to another by changing the order of a few arrows. These are not equivalent in terms of the conditional independencies. Now, if you're analyzing data which doesn't know anything about the directions, you can only discover the conditional independencies, so that the inference cannot distinguish those two. Sorry, cannot distinguish those two, but can distinguish these. Now, fortunately, there is a simple, easily understood test for Markov equivalence. Two DAGs are Markov equivalent if they have the same skeleton, that is, the same graph ignoring directions, and the same sets of unmarried parents, the same sets of immoralities, as they sometimes called. David's term there has had a lot of life. And what this means is if you want to conduct Bayesian inference using sampling methods on DAGs, what you have to do is operate on equivalence classes of of equivalence classes under Markov equivalence. And there's very recent work, and I'd love to see if this is going to be exploited in Bayesian computation, very recent work on Markov chains for completed DAGs that are guaranteed to be reversible and therefore potentially usable. Right, just to wrap up quickly, Bayesian structural learning is one of these beautifully simply stated problems. What could be an easier problem to state? But it's proven amazingly hard to deliver except on a modest scale. And that's true even with special choices of priors. When we first learned about MC, we thought, oh, now we're relieved, we can fit any model we like. But in order to make these methods work for even moderate-sized graphs, we start having to make special assumptions. And there's been a huge amount of effort on these problems from very creative people, many of whom are here. I mean, this is not a neglected area. As a result, we have a lot of heuristics work, a lot of relying on optimization rather than sampling. And to be honest, we don't really know what they're delivering. I mean, if a probability surface is hard to sample from, it's probably it's probably also true that finding an optimum finds us something that's very unrepresentative. I'm wondering whether it's time now to give up, if you like, but perhaps to refocus effort a bit. What we can estimate stably are edge occlusion probabilities and low-dimensional marginals. Perhaps the time has now come to really focus sampling methods on those and on theoretical work that tries to give us some sort of guarantees. And finally, I wonder whether the problems are hard. Well, obviously they are hard because they're discrete, but whether there's opportunities for relaxing the hard constraints and looking at weaker models. Thanks for your attention.